Okay, Team Bio, welcome to this week's screencast. It's on the movement of molecules. But before we start to talk really about the movement of molecules, I want to remind you a little bit about the fluid mosaic model of the membrane. Okay, so remember that this is a fluid mosaic model because all the pieces of this membrane are freely diffusing around within the membrane, both the phospholipids and also all the other things embedded within the membrane move around. It is fluid, and it's a mosaic because it's composed of a bunch of different things: proteins, cholesterol, sugars, and lipids. So the main function of the cell membrane is that it's a barrier. It keeps the outside of the cell out and the inside of the cell in. There's a lot of craziness happening on the outside of the cell, and the inside of a cell has to be maintained as a stable internal environment. This is called maintaining homeostasis. So the idea is to maintain a constant, stable internal environment amidst a crazy and changing external environment. And the way that the cell does this is it has this lipid barrier. But it's actually a selectively permeable membrane. I'm going to write that down. And selectively permeable means that some things can get through and some things can't. We're going to discuss this more in the coming weeks. Okay, so this is the background in terms of the membrane that you need to know. Let's move on and actually talk a little bit about chemistry and how molecules work. So molecular motion. Okay, imagine we have a brick of steel right here. And a brick of steel is actually composed of a bunch of little atoms of iron all in a nice and ordered sequence. And if we were to zoom way in and look at this on the molecular level, you would notice that each of these molecules of iron are actually vibrating around. They're jiggling and moving in space. They're not really changing in orientation relative to one another, but each of them is jiggling. So even in a solid, it's important to know that atoms are moving around while they're vibrating back and forth. So even in something that appears to be not moving, on the atomic level it is moving. Now if we were to compare this to, for example, a beaker full of water, this as well is composed of tiny little molecules of water, and these two are moving around, and the molecular motion of water is greater than that of a steel brick. So the molecules that make up the water are moving around faster and actually more. I want to just move it. It's not letting me move it all the way around. These molecules are moving around more than the molecules in the brick. Okay, and then let's take one last example. This is also a beaker, and it appears empty, but it's actually full of molecules of gas. And these are even less dense than our molecules of water or our molecules of brick, but they're moving around even faster than our molecules of water and our molecules of steel. So the craziness of the molecular motion of a substance depends on the state that it's in. And a gas is going to be crazier and more vigorous than a liquid, which is again going to be crazier and more vigorous than a solid. Okay, so all things have this inherent molecular motion. And let's look at another example of this. Imagine you have a jar of perfume. Okay, I had to pause that for a second to talk with a student, and I totally forgot where I was, but I think I was talking about this bottle of perfume. Okay, so perfume is actually a highly volatile substance, and so it's in liquid in the bottle, right? But it's actually constantly evaporating into a gaseous phase. So there are lots of little molecules, gas molecules of perfume that are in the air. And when the bottle's uncorked, then they leave the bottle and they form an area of very high concentration around the bottle, and then they also diffuse across the room. And so if you are a person with a nose, there's a mouth, yep. At one end of the room, you will smell any particle that enters your nose, and it's doing that because there's actually diffusion across the room from this area of high concentration, over here, and this brackets mean high, to this area of low concentration over here. And actually it's the second law of thermodynamics that tells us that everything trends towards thermodynamic equilibrium, which means that these molecules are moving from an area of high concentration to low. So what happens if you take the perfume and you cap it? Well, so you take this perfume here, and you're going to put a cork in it, and so now there's no more molecules leaving the perfume, and all we're left with are these molecules that are already out here in the room. Well, they're going to do something that's called diffuse down their concentration gradient. They're going to diffuse down their concentration gradient. And again, it's the second law of thermodynamics that says that all things are trending towards thermodynamic equilibrium, which tells us that these things are going to diffuse. And so ultimately the room is going to start to look something like this. Okay, so now the molecules have diffused down their concentration gradient, and now there is no more gradient, right? They're diffused equally throughout the room. So I'm going to erase this high and this low. So we have reached a state here of what's called dynamic equilibrium. And the reason why it's equilibrium is because there's no more concentration gradient. These particles are diffused equally throughout the room. So the probability of finding a molecule here is the same probability as finding a molecule all the way over here. So they've reached equilibrium. And it's dynamic because if we were to zoom in on any one molecule, let's pick this one right here, it's still moving around. It actually has the chance to go in any direction. And this molecule as well can move anywhere. So not only have we reached equilibrium, but it's a dynamic equilibrium, meaning that the molecules are all still moving around. But on net, they're going to move around the same. So we're still going to remain at equilibrium. But it's a moving equilibrium. Once we reach equilibrium, it's not like things stop. They're still moving around. They're just moving around equally. And that's a really important concept to know and understand. Okay, this brings us to the real meat of our screencast, which I'm going to put down here. Okay, so keeping in mind everything we've talked about so far, molecular motion, dynamic equilibrium, concentration gradients, here we have a beaker. And this beaker is full of a solution, a water solution. And a solution is composed of two different components. It's composed of water, H2O, which is the solvent. And it's also composed of salt, NaCl. So we have a saltwater solution here, and the NaCl is the solute. Some more chemistry words for you here. And together, they create the solution. Okay, in this solution, we have 98% water and thus 2% salt. That is the composition of this solution that we have right here. And you can assume that this is a fully mixed solution, so the salt particles are all dissolved in the solution, and they are at dynamic equilibrium, okay? Also, inside of this beaker, we have a cell. And inside the cell, there is a water solution, but of a slightly different composition. This also has H2O and salt, NaCl, but this cell starts out at 95% water and 5% salt. So slightly different than the surrounding solution. Okay, this cell is composed of a membrane that is selectively permeable. So water can pass through, H2O can pass, but NaCl cannot pass. A selectively permeable membrane. Okay? So, what happens when we have this scenario where the water salt concentration inside the cell is different than the water salt concentration outside the cell, but only water can move? This is an example where we are not at equilibrium, and all things trend towards thermodynamic equilibrium. So here, to balance out the concentration of salt and water, water is actually going to move into the cell here. And ultimately what's going to happen is this cell is going to get bigger. Oop, So, this cell gains mass and gets bigger as water moves in. And the concentration of water and salt inside the cell is going to change. Now it's important to note here that the number of salt particles inside the cell is not changing, right? Because salt cannot pass. Salt cannot pass. So the pure number of salt particles inside the cell remains unchanged. However, the number of water molecules increases, right? So, because water's, again, moving into the cell. So these numbers change. This is actually going to go up, and this number is going to go down, not because the number of salt particles are changing, but because the relative ratio of water to salt is changing. We're getting more water molecules inside the cell than there were before. This is a really important concept. If you don't understand this, please stop and watch that part again. Okay, so water will continue diffusing into the cell until the concentration inside the cell of salt and water is equal to that of the concentration outside of the cell of salt and water. And this is called osmosis. Osmosis is the movement of water. And this here was an example of a hypotonic solution. So I'm going to move down here for a second and talk to you about 3 different states. So this is a hypotonic solution. Oops. Okay, and in a hypotonic solution, the solute, which is the salt, to solvent, oops, forgot the L, solvent ratio outside the cell is greater than that of the solute to solvent concentration, I forgot the L again, inside the cell. So basically this just means that salt is low outside the cell and high inside the cell. In this case, water, H2O, is going to move into the cell. And this is an example of cytolysis. And cytolysis can be potentially very bad for a cell, because I'm sure you can imagine a situation in which the concentrations are so different that so much water moves into the cell that the cell bursts. That's the lysis part of cytolysis. Okay, so potentially dangerous situation, an extremely hypotonic solution. The converse of a hypotonic solution is a hypertonic solution. Let's do that right over here. Okay, so just grab this whole thing here, copy it, and paste it over here. So now, hypertonic solution, we're going to do some erasing. So erase, oh no, that was too much erasing. Okay, we're back to erasing. Okay, so in this scenario, a hypertonic solution, the solute to solvent concentration outside of the cell is actually greater than the solute to solvent concentration inside the cell. So now we have to change our concentration gradients as well. Now we have a higher concentration of salt outside the cell and a lower concentration of salt inside the cell. And so therefore water, H2O, is going to move out of the cell. And this is an example of what's called plasmolysis. And plasmolysis is also another potentially dangerous scenario for a cell, because it's basically a cell dehydrating. All the water's moving out of the cell. Okay, so we've got our hypotonic solution, our hypertonic solution, and the last one that you need to know is called an isotonic solution. And I'm sure you can guess, in an isotonic solution, the last case, just select this again, copy, and paste. Now, the solute concentration outside is actually equal to the solute to solvent concentration, or ratio, inside the cell, and this is an example of dynamic equilibrium. So, now we go back to our water, this example here. Imagine that the cell here is isotonic to the solution here. Water is still going to be moving into the cell, here, like so, but an equal and opposite amount of water is also going to be moving out of the cell. So, again, we've reached this state of dynamic equilibrium. Molecules have not stopped moving, but on net, they are moving the same. So isotonic solution is dynamic equilibrium. It's going to bother me if this is not at the same level as the other two. Oh, I can't fit them all on the same screen. Move this guy over. This one too. Okay, better. Okay, that is it for today. Yeah, okay. I will see you all in class on Monday.